Hey students, for good or bad, I thought I would throw together a little additional, and I'll call it supplemental information about chapter 36. Chapter 36 is always a big chapter, and we never have time to talk about all the details in class. And it was doubly worse this year, given that due to weather constraints, we had to close campus for 2 days and switch over to the video lectures. So I focused more on the physics, and I didn't really get a chance to get into some of the applications or some of the engineering, and I thought that was best. But on the other hand, I got to thinking as we're entering spring break here, I thought, maybe a good supplement for anybody who might be interested, especially because I think kind of the applications or the engineering gets people excited about it. And so we, spent all this time doing the physics, but we didn't really do any application. So that's what this supplement is. So you may or may not watch the whole thing, but I thought maybe I'd make a few comments now that we've got to the physics of our optics and say a little bit about the camera, a little bit about the eye, a little bit about what we just call a simple magnifier, magnifying glass. Then it's kind of nice to see how we would put these together, a couple of lenses, and we'll just put two lenses together here. And so we want to look at a compound microscope and a telescope. And maybe I should say then an astronomical telescope, not a terrestrial telescope, because we're going to see that ours gets inverted, which is fine when you're looking at the stars, not so great when you're looking at the mountainside. All right, so let's start here with the camera. In fact, I went ahead and printed up a nice picture out of your textbook here, kind of showing the general idea of the camera. And then let me take this as a moment to say 1 over P plus 1 over Q equals 1 over F. And so this is our basic physics that we said could be applied to lenses or to mirrors as long as we stick to these rules about when is the object distance positive, when is it negative, when is the image distance positive and negative, and when is the focal length positive and negative. We also, and just as a review, said the focal length is the radius of curvature divided by 2 for the mirrors, but the focal length, or at least 1 over the focal length, was a bit more complicated for a lens. It depended on the curvature of both sides of the lens. So in this camera, it would be each of these curvatures. And then, of course, what is the material made out of? Well, again, I'm probably going down the road too much of lecturing on the physics of it. But keep that in mind, because I'd like to apply this then to the camera. Let me put this page aside here and go ahead and say, if I were to rewrite this, so 1 over Q equals 1 over F minus 1 over P, you can kind of see something that is implied here in the math. And I'll come back to the picture. So this looks like we're trying to take a picture of somebody playing soccer. And so the light comes in, gets redirected by the lens. And I will say then that light has to be real, or excuse me, the image has to be real on the CCD array. It's the actual energy from this light that stimulates the electronics, or in old-fashioned case, the film. And it's that energy that makes the film material, the chemicals that are photosensitive, react. And so the silver nitrates and whatever they are in the old style film, or in this case, the CCD array, so the charge coupling device, the charges that build up in our semiconductors then are affected by this light. So this is the basic operation here of the camera, and the point is we have to get a real image. And you might remember us talking about the only lens that gives you a real image is this convex lens. The other one, the concave, made things smaller, right side up, and always gave us a virtual image. So we're not going to be able to use that for a camera because we got to get that light on the detector. And so, and in this case, we're going to flip it upside down. And that doesn't really matter inside of the camera. If it was old-fashioned film, then you would just have your film upside down. And then if you go to look at it, you just turn it over. And so your negatives are all technically upside down. Or if you turn them into slides, you put them in the projector upside down. So when they get displayed on the screen, they're the right side up. So again, the upside down is not real important. And in fact, it's actually really, really small. So what we want to make is this image from our object. And so here's P, the distance to the object, and here is Q. So Q is pretty small. And to do that then, if you come back here and look at the math here, actually maybe it was better to leave it as 1 over P plus 1 over Q equals 1 over F, because what I'm trying to point out here is the focal length of our lens is fixed. It has to do with the material the lens is made out of. It has to do with the 2 radii, and that's a fixed number. And so if somebody is trying to then take a picture, and maybe we'll just start with something really, really far away. So if you have like 1 over big for the object distance, you just get a 1 over Q and a 1 over F, and so Q equals F. And so you would then say that what you need is a focal length, probably 35 millimeters, from the lens to the CCD array. And so that's that distance, okay? Now, for things that are closer here, and of course at first, if it's just really big and gets a little closer, it's still really big, and so nothing really changes. But if P gets small enough, then you can't ignore this number. You get 1 over something, I'll call it medium. And so 1 over medium has some finite number, and that still has to equal this same constant. And so therefore, what happens is Q needs to go up a little bit. It needs to get a little bit bigger. So that 1 over this little bigger number is smaller than it was before. See, before, when we were focused at something really far away, we had an image distance the same as our focal length. I'll just call it 35 millimeters. But then, as the object got a little closer, or if we changed our attention to a little closer, the image is actually now a little bit greater than the focal length. You might write it mathematically this way. Q would be the reciprocal of F, then minus the reciprocal of P, and the reciprocal of that. Which again, if we go back and say if you're really big, you can ignore that, and then Q just equals F. But once you start getting things that are a little bit closer, you can't ignore that. And that's a little piece. And so you have this 1 over the focal length minus a little piece, which makes it a little smaller. So when you take the reciprocal, it makes it a little bigger. And so Q goes up a little bit. Which is why the way a camera is designed is that we would be able to then move this lens forward and back. And in this case, if we had it all the way back because we were focused on something really far away, then as that person got closer, we would, adjust the barrel. In fact, I've got my camera right here, and you can see the barrel here, and the lens then can move out. Now, to be honest, I use my iPhone these days for everything, so I don't have a charge on this one, but it was sitting there on my desk, and I go, let me grab that. But the idea here, if I could turn it on, but yep, I got to charge it. Hopefully it still works. And then the lens would come out. Or an old-fashioned one, I would turn the barrel. And that would screw the lens and make it come out. And so my point is that the way a camera works simply is using this equation. And to get it in focus on your film or your CCD array, the lens moves back and forth. And it goes all the way in, so the distance between the lens and the CCD is, at a minimum distance, the focal length. but then it can go a little bit further out, and as things get closer and closer, this goes further and further out. And then all cameras are going to have their limits. That is, they can't focus on anything closer because this can only go out so far. Now it's really too bad I didn't charge this up, because I'd like you to see mine when you turn it out, it goes out about this far. And so it can focus on things pretty close. I like this old camera. I need to get it out. In fact, it's at 36 times. But like I said, it just kind of moves in and out. In fact, you've probably been able to see this with the camera lens on my iPhone here. If I were to maybe put some small writing here and move it up towards the camera, the electronics inside is pushing the lens further out. And right about there, it looks like I've come to the limit. Let me back up a little bit. Yeah, so this is the nearest this camera can see. And so we might even say our cameras are far-sighted. They see things far away really well. But eventually, there's a limitation to them. And looks like right there. And of course, you can't really tell how close I am, but I'm probably guessing 4 inches or so. And so that's the best my camera can do. All right. There we go. Needed to move the lens and readjust. So that's kind of the first thing I wanted to mention. So I guess let me put a checkbox here. And now let's look at the eye, the human eye in particular. And you'll see it's not quite like the camera. Of course, it still has the same basic optic properties. And so if I kind of look at the eye, and so let me grab this picture. This, again, just kind of copied an image and printed it up from your textbook. And the light would come in from the outside world here. And the first thing it would do is hit the cornea right here. And that's part of the focusing. In fact, a significant part of it. You might even say most of it. But it's maybe not the most significant part of the eye, because that's kind of fixed. But then the light continues in and it hits this lens, this kind of clear material that, for lack of a better word, is kind of squishy. These muscles right here can push down and change the curvature of this lens. And so to use your muscles, you can, squeeze in and change that curvature. And these muscles, I'll probably say this wrong, cilia, but these eye muscles, the cilia muscles, push in, and of course you could get tired then, and you relax your eyes. So your eyes have a relaxed position, and so the muscle comes back and they relax. Now the big thing I wanted to point out is this is the huge difference between the camera operation and a human eye operation, because what we did in the camera was to move the lens in and out. The human eye differs in that sense, is that the image is going to be formed on the retina. So this retina is where the light makes a photochemical reaction and then sends that information down the optical nerve. And so this distance, which you might call the image distance, which is around 2 centimeters, it's obviously changes a little bit depending on the size of the person, but most human eye sockets are really close to 2 centimeters. I understand they don't vary very much. So a big person and a small person, the eye functions pretty much the same. But this is what I'm getting at. So if I write this equation again, 1 over P plus 1 over Q equals 1 over F, an important difference is this needs to remain constant, the image distance, not the focal length. And so all of our discussion a moment ago about how we would, for the camera, how this was a constant, and so as this got smaller, this had to get bigger, and so that these varied, and so as we focused on different objects, we changed where the lens was, so there was a distance, so that we always had this 1 over F that didn't change. But for the human eye, that's different. We want this to remain constant. And so you can kind of see here that for things that are really, really far away, and so I'm using the eye and I'm looking at something in the distance. Let's say I'm out in the wilderness and I'm focusing on a mountain really far away. And as I look over at that mountain, I would say, well, 1 over a big distance, and that is essentially 0. And so then I would get 1 over Q is equal to 1 over F, and if we run through the math, then that's just saying Q equals F. So when things are really far away, of course, this is the same mathematics as we did for the camera. The image distance, which is roughly 2 centimeters, is the focal length. And in a perfect working eye, that is what you get when you relax these muscles. And so the lens kind of flattens out a little bit. Still has some curvature to it, but enough so that the combination of the cornea with the lens gives me a focal length of 2 centimeters. And that's why, you call this the relaxed position. In fact, students are often told, hey, when you're studying a lot, take a break once in a while. Maybe, every 20 minutes or so, pause, look out the window, just let the eyes relax. And it doesn't have to be long. Just look out the window for about 5 seconds and then get right back onto it. And so then your muscles squeeze in. And that's what I want to say, is that if you are focusing on something close, like a textbook, and you're reading a textbook, or you're doodling your homework, and you're trying to solve a problem here, you're focused on something that's really not very far away, maybe 25, maybe 30 centimeters away. And so this number is smaller than the distance to a mountain. And then because of that, and this is to stay constant, this overall gets a little bit bigger. And because that gets a little bit bigger, right here, you want the focal length to get a little smaller. Smaller. And that's why I'm saying here that, again, as your eyes focus on something close, like reading a textbook or looking at the screen right now, your muscles here are making this bend more. Remember that formula here. And so to get a smaller focal length, we need a smaller radius of curvature. And our muscles need to clamp down and turn that more. So again, reading is actually using the muscles in your brain quite significantly. And so relax once in a while. But I think you're getting the main point and the difference then between how the human eye works versus a camera. I mean, we're still following this 1 over P plus 1 over Q equals 1 over F, but again, a big difference being that for the eye, you change the focal length of the lens, and I'll say the lens meaning the combination of the lens and the cornea. And then for a camera, you have a fixed focal length and you change the position of the distance. That's the big thing. Now, as long as we're here, we might well talk about, what can happen to the eye, good and bad, and particularly, why people need glasses. But maybe I will start with the cornea here. I don't know if you've ever looked underwater. You go underwater, you open up your eyes, and things are not real clear in focus. They're just not crystal clear. And of course, the reason for that is now you have water up against the cornea. And part of the bending of the light and getting it into focus is that transition from the cornea here, where it goes from air into salt water. So your eye, I'll call salt water. And so if you are swimming, and this is either freshwater or saltwater, there's not much of a difference. And what ends up happening is you try to compensate for this, and your eyes really squish down, but it's just not enough. And the images get formed way out here. And so by the time the light hits your retina, it's just blurry. It's not unreasonably blurry, but it's nothing like when you put a mask on, and so you put, or a pair of goggles, you just put something over the eye here so that the light comes in, and it goes from the water into air first, and then that way it transitions from air through the cornea, and now things look crystal clear again. And so a mask, a pair of goggles, even your hands cupped over your eyes and release some bubbles. You know, you can get kind of a bubble pocket in there and kind of see really well underwater. So that's the one thing I wanted to say. The other thing is you can then see what's going to happen with older people. As you age, everything kind of loses its elasticity. You notice that most in the skin. I mean, you can, obviously look someone in the face and you can tell, are they young or are they old? How tight is the skin? And the elasticity just wears out. But not only does the elasticity wear out on the skin, sadly, it wears out for this lens. And so this lens, the flexibility of it diminishes with age. And so usually in the 40s somewhere, maybe 50s if you're lucky, this ability to squish the lens, even though your muscles are still doing their thing, although I guess your muscles get a little weaker with age too. But it's not so much the muscles, it's the fact that this just gets harder and you can't squish it as much. And if you can't squish it as much, you can't really focus on things are close. And so you lose that ability to read things. And that's why people have reading glasses, is because they need a little more help bending the light. In fact, here's, my pair of reading glasses. They bend the light. They're concave. In fact, if you remember our discussion about them, and I guess maybe I'll come back to this, but you kind of see if I put it over here, they make things look a little bigger, just a hair bigger. So these aren't real strong reading glasses, but they are nonetheless reading glasses. And so a pair of reading glasses would be curved. And you probably wouldn't make it curved like that. You would probably go more curved and then less curved, so that they look better on your face. And this first surface makes it converge, this makes it diverge, but it converges more than it diverges. And so the end result is it's converging. And so that would correct for that. In fact, that might give me a chance to kind of point out then what your author talks about, people who are nearsighted and farsighted, people who are farsighted, and they can be, farsighted with age, as I was saying, but, you can also be young and farsighted, although most young people are nearsighted, they're not farsighted. But what's happening here in the eye is if you don't have enough curvature to, say, your cornea, then when you look at something far away, and so here's your cornea that's not very curved, and you have a lens. When you go to relax your muscles in your eye, because your cornea doesn't have enough curvature, something far away doesn't focus the 2 centimeters back on the retina. Now, you can make up for that by then squishing the lens and using your muscles. So things come into focus and you can see things that are far. But you're not really in the relaxed position. And so your eyes are always working hard, which isn't good. But also, what that means then is you've already used up some of your squishiness, if you will. And so as an object gets closer, and your eyes are going to have to squish your lens more and more, there becomes a point that you run out of squishiness, even when you're young. And so that was kind of what I was saying about old people run out of squishiness just because the lens doesn't squish anymore. But in a young person, this is squishing fine, but it's making up for the lack of curvature on this cornea. And so sadly, you have what you would call then a near point, where you could see things that were far away fine, but anything closer than that, you just can't focus on. You just don't squish enough. And that was what I was doing earlier with kind of this piece of paper going up to the camera. It's like, look, at some point, you just can't focus enough. Now, maybe that's a bad example because the camera and the eye are a little different. And anyways, so you have a nearsightedness. So, I'm sorry, you have a near point. And so you can see things far, and hence the name farsighted. So if you wanted to correct it, and that's what this image is trying to show, is you would put the same type of glasses on somebody like these reading glasses. They need help converging the light because this cornea doesn't do it enough. Now, like I said before, you probably don't want to put a lens of this shape, a biconvex lens. You probably want to put one that's got a little more curvature of convex and a little less concave. So it's a convex concave, and that's how these reading glasses are. There's a concave here and a convex here, but it's more convex here than concave there. So the net result is focusing the light. And so this would correct somebody who's farsighted, and that's what your author is trying to point out here. We have a converging lens that helps them so that they can see things. And then that way also, when they look at things far away, their eyes can go in completely relaxed mode. And of course, laser surgery, you would go in here to the laser and you would trim up the cornea a little bit. And give it that curvature that it needs. And then everything's fixed, and so you don't need the glasses anymore. And so that's how the laser surgery works. Although I guess I should say there's other reasons to be farsighted. But in the kind of the description I was saying, that's what you would go in and do the laser for. And then you can see the same thing for somebody who's nearsighted. And that would be me. I'm nearsighted. And so what that means is I've got too much curvature to my cornea. And so from things that are far away, the light comes in and they hit my overly curved cornea, and I can relax my eyes all I want, get in a full relaxed position, but sadly the light still focuses before it gets to my retina. So by the time it gets to my retina, it's past and started to get blurry again. And so when I look at things far away, they look blurry, and I can't fix that. I can't relax my eyes anymore. And they're just blurry far away. And that's called nearsighted, though, because as things got closer, I would need more curvature. In fact, I wouldn't even have to use the muscles. At some point, I would get right, about here, let's say. And they would be in focus. And I haven't even started to use my muscles to squish it. And then, of course, if things got closer, then I could use my muscle in my eyes to squish. And so I see just fine things that are near, right? And hence the name nearsighted. And when I was younger and nearsighted, I could see really close, because then I could just keep squishing my lens. Now, sadly, as I've gotten older, my squishiness has deteriorated, and now I need reading glasses for things up close. But for most people, I needed it a little later in life because I had this, I guess if you want to call it an advantage of being nearsighted, I didn't, my extra curvature here of my cornea kind of helped. Anyways, that's why in this picture, they call this then a far point, because there's some point that is the furthest you can see. And so you can see all this stuff in here. You're nearsighted. And so to correct so that you can see it, you would want to put a type of lens that would make the light diverge. And so we got a diverging lens, and that's what the author is trying to show in this picture. Now, I drew a double concave lens. That doesn't look good on somebody's face. So this is probably a better lens where you have the first curvature, which is the convex one, not as curved as much as the second one. And so that fits better on somebody's face. In fact, it makes it thicker on the ends than in the center. And that's why you can kind of see these when you look at the side of somebody's glasses. They'll be thick. In fact, when I was a kid, that was, we called these the Coke bottle glasses, because they were just like the bottom of a Coke bottle, which I know Coke bottles aren't made out of glass anymore, but when I was a kid, they were really thick. And so these are thick. And so here, I'll just take the ones off my face, not to confuse them with my reading glasses, but mine you can kind of see they're a little thick. I'm not that nearsighted, and also mine are a little thinner because I've paid extra for materials that they call high index. So when it's high index, the bending comes from the high index. Remember, the equation for the focal length had an n in it as well as the curvature. So it's that, 1 over focal length equals n minus 1 times 1 over R1 minus 1 over R2. So in my case, I paid extra for a high index. That way the curvatures didn't have to be so much. And then that way they kind of look light. And that's what I wanted. So that's what I paid for. And so I had to just shell out the extra money to get them. But I also got them polished on the edges too, so that they don't stand out and look so thick. I guess those are just childhood scars of being, Coke bottle glasses. So that's this whole idea of this index there. All right, so that being said, then the laser surgery would come in, and like we said, for somebody who's farsighted, nearsighted would come in, and they would kind of trim up the cornea. And again, get it to its correct curvature. So that's how that works. All right, well, I hope that whole discussion of, lenses and glasses and the eye kind of work here. Let's keep going, because then I said, let's see, got my papers all over the place. Where is it? Here we go. So after looking here at the functioning of the human eye, although I was thinking there was one more thing I wanted to say about the human eye, but nearsighted, farsighted. Oh, I know. I wanted to kind of show you, see if you could see it here. So you would see, if I kind of go over these words, telescope, I hope you see it. It makes it just a little smaller. Maybe a little bigger, like this word that says image here. If I just kind of slide over, you can see it makes it just looks a little smaller. Whereas if I slide over with the reading glasses, it makes it just a little bigger. Which, by the way, I always find it interesting, and you can really tell somebody who is farsighted versus nearsighted, especially if they're very farsighted or very nearsighted, because somebody who's farsighted, they're using a converging lens to correct their vision, and somebody who is nearsighted, like myself, is using a diverging lens. And so diverging lens, this is one I said is the boring one, it makes things look smaller and upright, whereas the converging lens makes them look a little bigger. Now you can see that kind of nice there. Yeah, smaller. But it also looks in the reverse. And so when I have these glasses on my face and somebody looks me in the eyes, they're actually seeing my eyes a little bit smaller. And that's disappointing to me because psychologically people associate friendliness with bigger eyes. And so people who are farsighted, I'm kind of jealous. You look in their eyes and they just look so big, especially if they're really farsighted. They're so big and friendly looking, these big eyes. And it's like, wow, you got gorgeous eyes. And then you look at somebody like me who's nearsighted and you look at their eyes and you go, oh, you look shady. You look dangerous. You got little beady eyes. So the type of glasses you wear can, affect what people see in terms of your eyes. Okay, so enough of that. Let's move on then to here, the simple magnifier. Now, the simple magnifier, I think I printed up a page somewhere here of the simple magnifier. Here's the page I printed. I think I have a magnifier. Let me jump over here somewhere in my desk. I thought I had. Yes. I always keep a lot of fun stuff handy. But here we go. Here's our simple magnifier. And then actually this one is even a better one. It's got more curvature to it. And you can see that if I trace it over things, they look big. This one makes them, hopefully looks bigger too, but I like how wide the diameter is on this, but I like the strength of this one. So maybe I'll use this one here to show you. But remember when we talked about lenses then, we said that this lens, the one that has this shape, the convex, can make things look bigger. The other lens can only make it look smaller. Now, this one can actually make it look smaller too, depending if you're looking at something far away. But when you look at something close, it looks bigger either right side up or bigger upside down. And if it's really close, like I'm trying to show you here, it looks bigger. Maybe I'll pick on that 25 there. And when you look at that 25, it looks bigger and right side up. Okay. Anyways, so this is the simple magnifier. So let's talk about the simple magnifier. And to do that, we do have to kind of introduce you to something a little new and different. Because if I just had a lens with a focal length, and if I put the object within the focal length, as we talked about in class, the ray would come out and go through this focal point. We could say the one through the center would be undeviated. The one that has the same angle as coming from focal length would then go straight. All three of these can be traced back to here. And so our image here, so this is the Q, and then this is the P, and this is the height of the image. And this is the height of the object. But we would have an image that is right side up and is bigger. Okay. And so we called this capital M for magnification. We said the height of the image compared to the height of the object. And we worked out that it was equal to negative Q over P. Now, I did not use the phrase lateral. Let me use it now. But this is really best described as a lateral magnification, because it made it bigger. But see, it's also making it further away. And that means seeing details may or may not improve. And so keep in mind that lateral magnification is just saying how big is it, but it could be far away. See, if you wanted to see some details, oftentimes it's not so much how big the object or the image is, but how much angle can you focus on? See, that's where your author's picture comes into play. And so your author says, let's say for a moment you don't have a magnifying glass. Let's just say that you are looking at it. So here's your eye, and here is the object you're looking at. How much angle does it, excuse me, does it spread out in your face? Now, the reason the author put 25 centimeters here is, remember, as we said earlier with the human eye, that you can only get so close, and then the squishiness of your lens doesn't get it into focus. And 25 centimeters is a good human average. Usually young people can do a little bit better than that. And as I said, if you're already nearsighted, you can even do better than that. But let's pick as a general discussion then kind of what people in their 20s probably do, maybe late 20s, is they can focus on things, at 25. In fact, it might be fun just to, take some small writing and lift it up closer and closer and closer and closer and closer to your face until it gets blurry. And then you'll have an idea of what your nearest point is. But in general, we like to say, let's call this 25. Okay, now the reason this is important is, let me call this then theta naught. This is the angular spread I could see without a magnifying glass. Now, let me use the Greek's definition of an angle. It would be the arc length over the radius. So I'm going to come over here and say this angle naught would be this distance, which is h, which is kind of close to the arc length. And the radius out would be the 25 centimeters. And so I'm going to just say, okay, like I said, let's call that theta naught. Now, this picture is showing what would happen if you then put a magnifying glass in front of it. And so we set it at a point that's kind of close to the focal length, but it's got to be a little closer than the focal length, because that's going to make an enlarged image. And so the light from our image would come out here. And so you could argue then, as the light comes in, this human over here is seeing this angle, which if you trace back to here, which if you extend out, then that would be, and I'll call it theta. And this theta, if you will, well, maybe for starters, I'll call it the height well, yeah, let me do this triangle here. And so it is the height of your object divided by P. Because I want to take then a moment to introduce you to something a little new. It won't be on the test because this is a supplemental lecture. I don't think I assigned any homework. Maybe I did from this. But let's call this the angular magnification. How much better or bigger does it spread out now compared to what it did? And so it's an angular magnification. And so that would be this h over p divided by h over your near point. Again, call it 25. Which, of course, when you simplify this, the 25 goes on top and the p goes underneath. Now, the reason this can be really big is because when you think about here with your human eye, back here, you're looking then at a p that can be kind of small, much under 25, and so this number is greater than 1, and so this helps. In other words, what really happened here is the image got pushed back. See this 25? And so the light is equivalent of coming back here because you have to, for your eye to focus on it, it has to be the equivalent of coming from something far away. Something that was actually this short distance, maybe 2 or 3 centimeters, your eye couldn't have focused on. That's why you didn't bring it any closer than 25 without the magnifying glass. And so here, you might say what I'm really doing is I am taking something and getting it close, but using the lens to redirect the light so that it appears to be coming far away, because if it appears to be coming far away, my eyes can focus on that. And so I need to get it at 25. So here's why I say that, because if I write 1 over p plus 1 over q then is equal to 1 over f, where f then is the focal length of this lens, then I can solve for p by saying my goal of this magnifying glass is to get an image that is 25 centimeters away. And then that will allow me to solve for what p is based upon the focal length, and then I can put it into here. And so I'll give that a try. And so, let's see. To solve this for p, I guess I'd go 1 over f minus 1 over 25 is equal to 1 over p. Maybe I'd get a common denominator of 25f, so this becomes 25 minus p. And then I would invert it, and so I would get p equals to 25f over 25 minus p. Minus f. Minus f. Okay. So there is what p needs to be, like I said, in order, based on the focal length of this magnifying glass, in order to get the image to be out this at my near point. So I can actually focus on it. And so let me use this up here, as we said. And so I would say then my angular magnification, and so we like to use the symbol lowercase m for the angular magnification, as opposed to the capital M, which is the lateral magnification. And in fact, maybe I'll do it here. So my lowercase m then would be 25 divided by this p, and this p then would be 25f over 25 minus f, which, when we simplify this, we get the 25 minus f on top. The two 25s cancel off, and I get an f down here. There should be a plus sign. Did I mess up? Oh. Shoot. This is a negative number, and so I should have put negative 25. There's my mistake. I was trying to see how best to write it, but remember your sign conventions. And this is a good example of how easy it is to kind of screw up. Because we think in terms of magnitude, but remember, it's a virtual image. And so the light comes in, the light actually goes here. So this is our image on the virtual side. This is where the light doesn't go. This is a negative 25 when we put it into our equation, which then makes that a plus, which makes that a plus, which makes that a plus, and then that's what was bothering me. That should be a plus because the answer, which I've used many times, I know, is 1 plus 25 over f. And so that's the angular magnification from just what we call a simple magnifier. That's what we call the best you can do. Now, I'll even give you one more. Sometimes we call this then M max, so the maximum you can do. There's also sometimes what we call relaxed. Because if we come back to our picture, remember, we said, well, why don't we do this? Why don't we just say, hey, make this object appear to be coming 25 away. But remember, 25, our eyes have to work kind of hard. So if we wanted our eyes in a relaxed position, let's make this really far away. So if we come back here and think about this math again, 1 over p plus 1 over q equals 1 over f. And we want the image from this lens to be really far away. This then would be 1 over big. And actually, I can even put negative big so I don't mess up my sign again. Although 1 over a positive big and 1 over a negative big, I'm still going to just say is 0 and negligible. But then you get p equals to f. And then if you take that back to here, which we got our angular magnification, we can say then it is 25 over just the focal length, which is this back term. And that's most of the magnification anyway. So if you have a small focal length here, maybe, even a small focal length of 5, which isn't that small, 25 divided by 5, that's 5 already. And you could get up to 6 if you're willing to use your muscles in your eyes. But just in a relaxed position, you would have a magnification of 5. And that's really nice. You could even go smaller. This could be a 10 or, 1 centimeter. This is a magnification of 25. And really then, to make your eyes work hard, to go from 25 to 26 just isn't worth it. And so many times we say, let's shoot for this, especially if we're using our eye to see what's going on and focus on it. And that's what this is designed for, the eye. That's where the 25 came from. So most of the time when we do our calculations, we have this 25 over f for what is the angular magnification when you're in the relaxed position. Now, again, the reason that's going to be kind of important here is because now, knowing that, I can magnify things in the relaxed position, depending on what this focal length is, I could then build a microscope. And so let's build a compound microscope. And your author does a good job here of saying, well, here's what a microscope would look like. You would take something that's really small and you would put a lens We call it this objective lens because it's near the object. It would redirect the light, make an image, and then we would have a second lens. And the image from the first one now becomes the object for the second lens. And the second lens we call the eyepiece. And the microscope then has a tube body of L. And so we put, the object lens near the object. Usually this is like, if it's a microscope, we've got a microscope slide right here. And then there's a tube for the optics, and then there's an eyepiece, and somebody comes up and puts their eye really close to it. And when you try to understand, what is the working of this, and, how does it work, what is the goal here of this compound, so it's called compound microscope, it's got two lenses. You might say that the magnification total that I'm after really would be made out of two pieces. And I'm going to put a capital M and a little m, because here's the idea, is that I'm going to use this first objective piece really to make the image right here from this object. And I'll try to make that as big as I can be. But in addition to that, I will use this eyepiece, which I will just think of it as a simple magnifier now. And saying, okay, I'm just going to use the simple magnifier and see how big I can get it. So in other words, this right here is really going to be my 25 divided by the focal length of my, and I'll put a little e for my eyepiece. And so that's kind of the thinking of this compound microscope, is I'm going to use the second lens, the eyepiece lens, as a simple magnifier of this first one. And of course, then I'm also going to magnify this. And then here's where I can do some approximations. And I'll admit this is not, perfect engineering in a sense, but it's very, very handy and very, very useful. And that is to say, something like this, that if we're, using 1 over P plus 1 over Q equals 1 over F, and we're trying to make this image big compared to that, it's nice to then, and I'll put magnification minus Q over P. We're really trying to get this P here somewhere near the F. So I'm going to say this is approximately the focal length of the objective piece. Now, we have to make a real image over here for the eyepiece, so you might argue, well, then it technically has to be a little bit further. Not inside, not like the simple magnifier. It has to be a little bit on the outside. So technically that's a little bigger than that. But watch this. If I'm trying to get my simple magnifier to make it as big as possible, again, I'm trying to make the distance from the image of the first one, which is the object for the second one, about the focal length. Maybe a little less, as they show, but it's really close. In addition to that, since I'm trying to make it really big with the eyepiece, I'm also trying to make my focal length really small. Remember, we said that the magnification depended on that focal length. And so it would be nice to make that really small. And so, not perfect mathematics in any way, but as a ballpark approximation, I could say that the image from the first lens, which again becomes the object for the second one, is pretty much the length of the body tube of my microscope. Not exactly. The body length of my microscope is probably pretty long, maybe, 25, 30 centimeters. But the eyepiece focal length is probably well under 1 centimeter. So it's 25 minus, a half or 2/3 of a centimeter or something, maybe even less than that. So really, it's very close to the body length here. And so what I'm going to do is say, let's take this and replace the image distance from this first lens as approximately the body length. Now, it should be a little shorter than that, so I actually made this a little bigger, but that's what I also did down here, right? So, again, a little bit off per se, but not bad. So I'm going to say that we could call the lateral magnification of the objective piece to be roughly a minus L over the focal length of the objective piece. So as a rough ballpark, and quite reasonable, perfect, no, but practical, yes, equation for figuring out the total magnification, and it would really be an angular magnification, is to say that the first lens makes it bigger laterally, and the second one acts as a simple magnifier, which gives me a bigger angle. And that's really what I want. I don't care how close the thing looks or even how big it looks. I want to be able to see details, and I want it to spread out and be a big angle in front of my face. And I actually want it to appear far away so my eye doesn't get tired. And so I'll use the relax angular magnification. So if you put all these together, we have kind of a working equation that any of you who've worked with microscopes have probably done, that the overall magnification depends on your two focal length of your two eyepieces. I mean, your two lenses. One is an object lens and one is the eye lens. And you want those small. So you want this denominator small if you want to really magnify it. And then also, microscopes that got really long body tubes, your L gets really big, and that can help with your magnification. And so by making your microscope with a big body tube and two small focal lengths, you can get a lot of magnification, 400, 500, 600, 1,200 times bigger. All right, well, I've probably been blabbing on too much. Should I do the last one? I'm just past an hour. Why not? Why not? Here, okay. So last one, the fifth one that's kind of fun to talk about is the telescope. The telescope's a lot like the compound microscope in the fact that it has two lenses. So in terms of the engineering and the physics, it's a lot the same. However, the goal, maybe not the goal, the objects you're looking at are very different, and that makes it for a different design, because on a microscope, you're looking at things that you can get very close to your objective lens. For the telescope, you can't get close to it. When you're looking at the moon, it's far away. When you look at Jupiter, it's still far away. You look at the sun, it's still far away. We really don't have the ability to get close. And so our first lens, we're always going to be thinking of the object as far away, which probably explains then why we end up with a different design and a different thought process and, of course, a different formula for the magnification of a telescope. You might do this. You might say, okay, here is, again, my objective lens and my eyepiece lens. Okay, so I got my two lenses. And the thing I'm looking at, and this picture from your author, he probably should have put something out here. Let's say I'm looking at the moon. And so the light comes in from far away, and so by the time it gets to your telescope, it's parallel. I mean, it's not spreading out. I mean, the moon, 240,000 miles away? I think I just saw a little bit less than that, 238 something thousand miles away. And so really what we want to do is be able to see like the surface of the moon better. And here's where it goes a little different. We don't actually want to make the moon appear to be bigger. We want to be able to see details better. In fact, the moon's already pretty big. There's no point in having a lateral magnification. In fact, you could argue that a telescope does not magnify the moon. It actually makes it smaller. It makes an image of the moon, and that image is many, 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 many times smaller than the moon. The moon is ginormous. You know, what is it, 1/6 the size of the Earth or something? I mean, it's huge. And so when you get an image of the moon that's in your telescope, it has actually been reduced dramatically. However, what makes it nice to see the surface of the moon is that even though you dramatically reduced its size, you put it closer to you to observe. And so your angular magnification, the details of looking at the surface are easy to see. And so we need to talk about the angular magnification for a telescope. Just like we did for a microscope, but the first lens, we needed to talk about how it made it bigger, and then we spread out the angle. Here, the objective piece really can't do that. In fact, it doesn't make it bigger. It makes it dramatically smaller. In fact, you might even argue 1 over P plus 1 over Q equals 1 over F. And if you say that, you know, the P is really, really big, then you get a Q that's equal to an F. And then if the lateral magnification, where you say minus Q over P, you get a minus F over big. And if you take that too far, big, and you go, well, that's 0, then yeah, the size of our image from the objective lens is 0 in size. Now, it's not actually 0 in size, and that's good, because if it was 0 in size, there would be nothing left to magnify with the eyepiece. But it is really, really small. And so that's why I say telescopes don't really magnify things. We don't want our image of the moon to be bigger than the moon itself. We want it to appear closer to us so that we can then focus in and get close to this image. And that's what this eyepiece is going to do. And so I guess I'm going to use this argument here that if I was, you know, looking out at the moon, here's the light, and it makes this angle theta naught. So that's the best I can see without any optics. But then, with my optics, I made an image of the moon from this objective lens right here. And then the eyepiece made another image. And so remember, the second image is from this eyepiece, which the image of the first one becomes the object for it. And so the light comes in and is redirected, and so we'd call that theta. So the second one actually then makes it go out a little bit further, actually quite a bit further. Minimum, we can do our 25, but then our eyes would strain. So when we're looking in the telescope, we want this to be really far away, but also really big. Anyways, that's kind of our goal of our telescope, to see how much have we increased our angular view of the moon compared to what it would be without any optics. Okay. Now, if you want, I guess I would say then this theta, you know, would look something like this. You can kind of see it in this picture. Actually, maybe I should start with the theta naught. So the light comes in from the theta naught and makes an image right here. And so this angle, theta naught, is basically this h prime, the height of the first image, the image from the objective lens, divided by this length. And since we're looking at something really far away, so back to here, this image distance, q, is essentially the focal length of the objective piece. So this would be over the objective piece, f of the objective piece. Now, following this ray diagram, and maybe a little quicker so I can wrap this up for you guys, but here the author has drawn a light coming in and then turning here. And of course, this light is coming in parallel to the optical axis. So it should go through the focal point These other ones wouldn't. But when you trace them back, that's why you get something that looks really far away, but also really big. But we can use this angle here to say, okay, well, that angle would be the height of this h, which is the h prime, which is the image of the first one, which is now my object for my second one, and then the focal length of my eyepiece. And then that way, the two h primes cancel off, and you get the focal length of your objective piece divided by the focal length of your eyepiece. And so that's a little different formula than the microscope. What I do with my paper for the microscope. Oh, I don't know. That's crazy. All right, well, anyways, it was this. Whatever I did with that paper, it should have been for the microscope minus L25 and then the product of the two. And so you want both of those small, but you want L big. And then in this case, you want the focal length of your objective really big, and then this one small. And so that's why, and it's kind of really the sum of those two is the length of your body. And so it does help to have a long body, but the real magnification is not so much in the length of the body, but how the length of the body is cut into the two pieces. All right, well, I'll call it quits, and hopefully this was a little application stuff and kind of interesting on using the different optics here. All right, take care, everyone.